How might you prove a statement like the sum of numbers, or the sum of all the numbers from 1 to n is given to you by the formula n times n plus 1 over 2? Hello, welcome back to the Quant Plus YouTube channel. Today, we're going to be discussing induction, proof by induction. Before we do that, let's dive into the formula that motivated this particular video. As the story goes, when a particular mathematician was a child, he had a math teacher and figured that giving that mathematician the task of adding the numbers 1 to 100 would take up some time and give the teacher some free time to do whatever they wanted. I believe the mathematician in the story was Gauss, although I'm not particularly sure. Regardless, apparently Gauss figured out this formula, n times n plus 1 over 2, and told his teacher, oh, well, the sum of numbers from 1 to 100 is 5,050. Well, that formula is great and all, but let's demonstrate why that's the case. The technique that we're going to be using is called proof by induction. Now, I'm including this video in the calculus playlist because this idea is often introduced in analysis courses where you're building up the real numbers in a rigorous way, and you're then using that to demonstrate some of the ideas in calculus such as continuity, differentiability, limits, and so on. And the general idea of proof by induction is that you demonstrate whatever thing you want to show for some base case. Often it's the scenario where x is equal to 1 or n is equal to 1. Then you assume that the statement is true for some arbitrary value of n, and then you demonstrate that this given statement holds for n plus 1. Now, to backtrack a little bit, the natural numbers can be thought of as the positive integers, right? So 1, 2, 3, and so on. And part of the reason that proof by induction works is because you can think about the natural numbers in terms of a recursive relationship, with your first value in the relationship being a1 is 1, and then every subsequent value is determined by adding 1 to the previous value. So as an example, you get to the natural number 2 by doing 1 plus 1 is equal to 2, and then you do 2 plus 1 equals 3, and that's how you get your third natural number of 3, and so on. So by demonstrating that something holds for a base case, let's just say n equals 1, and assuming that it holds for n, for some arbitrary n, and then showing that if it holds for n, it implies that it holds for n plus 1, you're in turn actually showing that it holds for all the natural numbers. Now, jumping to our particular example, let's prove that the sum of numbers from I equals 1 to n is given to you by this formula n times n plus 1 over 2. Now, kind of referring to the steps I wrote down previously, if you're following along, the first step is our base case. In this particular scenario, I want to show that it's true for n equals 1. Well, the sum of numbers from I equals 1 to 1 of I is 1, right? Because the sum of 1 in itself, 1 is the only value in our sum, and therefore our sum has to go to 1. And what does our formula get us? Well, n times n plus 1 over 2 is 1 times 1 plus 1 over 2, which is 1 times 2 over 2. And this is actually equal to 1, showing that this formula holds for the base case. Right, so just for sanity's sake, I'm going to put a little check mark next to the base case. Step 2, we're going to assume that it holds for some arbitrary n. Right, so we're going to assume that the sum from I equals 1 to n of I is n times n plus 1 over 2. And now step 3. let's show that if this formula holds for n, it also holds for n plus 1. So, show for n plus 1. So the sum of numbers from I equals 1 to n plus 1 of I can be rewritten as the sum of numbers from I equals 1 to n of I plus n plus 1. Well, according to our assumption, this sum should be n times n plus 1 over, n times n plus 1 over 2 like this, plus n plus 1. And then by creating a common denominator and expanding our parentheses, we get to n squared plus n plus 2n plus 2 all over 2. Then, by combining like terms, we get n squared plus 3n plus 2 over 2. And by factoring the expression in the numerator, we can write this as n plus 1 times n plus 2 over 2. Well, if we evaluate the given formula at a value of n plus 1, then we get n plus 1 times n plus 1 plus 1 over 2, and this can be rewritten as n plus 1 times n plus 2 all over 2. And so in step 3, we showed that assuming that this formula holds for some arbitrary n, it also holds for n plus 1, and therefore our conclusion is that the formula for the sum of values from I equals 1 to n is indeed n times n plus 1 over 2 for all n. Now, once again, I introduced this idea in terms of an example in the natural numbers, and I'm putting this in the calculus playlist because it ties to analysis. But this concept can be introduced in many other scenarios, right? This is a concept that you can leverage in discrete math. This is something that you can use in linear algebra, and it kind of makes sense to discuss in terms of linear algebra because it relates to the idea of like the dimensions and coordinates of a subspace. And you can also leverage this concept outside of purely mathematics, right? You can demonstrate that this is applicable in statistics, economics, physics, and numerous other fields that are related to mathematics. So to summarize the findings of, or not to say the findings, but to summarize the concept of today's video, one important technique that you can use to demonstrate or to prove something rigorously is proof by induction. And in general, what you want to do is that you demonstrate that it's true for some base case, often n equals 1, but can be any other like starting point, really. Assume that whatever statement holds for some arbitrary n, and show that assuming that the statement holds for some arbitrary n implies that it also holds for some n plus 1, demonstrating that whatever statement actually holds for all the natural numbers. If you found this content informative, please support the channel. You can do that by liking this video, sharing it with your friends and family, subscribing to the channel, and honestly, if you have any concepts you'd be interested in, I would love to see those in the comments as well. Lastly, if you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.